Okay, this is Chapter 3, Control Volume Analysis, Part 6. You'll notice that I'm breaking these videos up into smaller and smaller chunks, hopefully to make them a little more digestible. So in this video, I'm going to continue talking about the linear momentum equation, and we're actually going to do an example, this example here, of calculating the forces in these bolts that attach a nozzle to a pipe. So this is going to be a water nozzle. Now, part of that calculation involves calculating the net pressure force on a closed control surface. And I'm going to talk about a trick really about how if you convert pressures to gauge pressure, that can make that calculation a lot less complex. And once we've done that discussion of the net pressure calculation, we'll go on and do a fairly detailed numerical example. So as I said, in the application of linear momentum, often we have to calculate pressure forces on the control surface. Certainly that's one of the forces that comes into play in many examples. Pressure acts normal to the control surface and it acts inward. Remember when we did the hydrostatics, pressure always acts normal to the surface and inward. And if I go back briefly here to the previous slide, you'll see I've drawn here sort of an arbitrary, your standard potato-shaped control surface, sort of meant to represent an arbitrary shape. And remember, the unit normal vector here points outward by definition. So if we want to calculate the total force through integration, the total pressure force here, we have to integrate PdA, but the minus n accounts for the direction. N points outward, so minus n means that you get a pressure force that is inward, where P in this case is the absolute pressure. Now you'll see later on when we start talking about this nozzle that this integral could be quite difficult to evaluate if you have a complicated control volume or control surface. But luckily there's a trick that allows us to simplify this. By working in gauge pressure, I'm going to show you that this makes the calculation of the net pressure force much easier. Okay, so we start by considering an arbitrarily shaped closed control surface with a uniform pressure on its surface. And that's the picture over here on the right. We have an arbitrarily shaped control surface and we have a uniform pressure, and we're going to call that PA. Think of it as the atmospheric pressure. So now we integrate that atmospheric pressure integrated over a closed surface. So in 2 dimensions, it would just be a closed curve. In 3 dimensions, it would be a closed object. So nothing with a hole in it. We have to consider the entire surface area of the object. And if we integrate the pressure, a constant pressure over a shape, we're always going to get 0. For a closed surface, there can be no net pressure force, no matter how complex the shape, provided the shape is completely closed. Let you think about that for a moment. How do we know this? The book gives this expression and doesn't put a sentence in to justify it. And it's probably obvious to some of you, but maybe some of you are puzzled by why that has to be. Well, the reason is nature takes care of that force balance for a closed surface. We know that because objects that are sitting around in the room don't spontaneously move because of an imbalance in pressure force. The coffee cup on your desk, which is a very complicated shape, has atmospheric pressure on all sides, and nature takes care of the integral. There's no net pressure force in any one direction. It's completely balanced. So we know this is true just from our everyday experience. Now we can use this convenient fact to simplify the net pressure calculation when we have a more complex pressure distribution. So now consider, again, this arbitrary control surface here. But now we have sections of the control surface where we have a non-uniform pressure. So again, the total pressure force here would be the integral of the absolute pressure integrated over that complicated shape, and then again the minus n is to take care of the direction. Now, turns out we can simplify this problem by subtracting out the uniform pressure. So I've rewritten this and I've added minus PA. So this is the absolute pressure P, and PA is the uniform atmospheric pressure. Now remember from chapter 1 and chapter 2 that P minus PA is the gauge pressure. Remember that Borden gauge that we talked about? So this is gauge pressure, and so we can rewrite this as the integral of the gauge pressure over the area. This is equivalent because we've subtracted off the integral of that uniform pressure. We subtracted off basically PA dA, the uniform, and we know that integral is 0, so we haven't changed anything. So the result is that we can integrate only over regions with non-zero gauge pressure. So we don't need to integrate over the entire object. We just need to perform the integration over these regions where we have a non-zero gauge pressure, and that makes the calculation much less complex. Here's an example from your book. I'm going to talk about the example, but it's not a complete impulse momentum example. It's just talking about the pressure force. And what it's talking about is a nozzle here. This is a different one that we're going to do. We're going to do a different nozzle in a few moments, a more complicated problem. But just consider a nozzle where we have flow in from the left, and it's coming in at 40 psi, and it's discharging to atmosphere. Of course, it would speed up. The water, if it was water, would speed up as it went through that nozzle. And the outside of the nozzle is exposed to atmospheric pressure. So if you were to try to integrate to get the net pressure, you'd have to include, if you wanted to work in absolute pressure, you'd have to include this complex integration of the atmospheric pressure over the outside of the nozzle. So this is the complex problem, but this is B here is the equivalent problem where we subtract off the atmospheric pressure, which applies over the entire control surface. So the integral of the atmospheric pressure over the control surface is 0. So the equivalent is just we can have no gauge pressure on the outside of the nozzle or the exit of the nozzle, and we only need to consider the non-zero gauge pressure at the inlet. So to get the net pressure, we just need to calculate the integral of the gauge pressure at the inlet. So that's 25 psi, pounds per inch squared, and you're told in the problem that this distance here, the diameter, is 3 inches. So pi d squared upon 4, and you get 177 pounds, and that's the net pressure force on the nozzle. So I think you can see from this how this trick makes it much easier to solve the pressure force part of linear momentum problems. Okay, so now we've got this under our belt, let's do a more complex example. This is almost as complex as they get. Water at 20 degrees C flows through a nozzle at a steady flow rate of 0.60 liters per second. The nozzle inlet and outlet diameters are 16 and 5 millimeters, and I've shown them over here. There's at the inlet, and there's the nozzle outlet. The nozzle has a mass, so the metal nozzle has a mass of 1/10 of a kilogram, and the water contained in the nozzle, so just in the nozzle section, has a mass of 3 times 10 to the minus 3 kilogram. So we're not going to neglect gravity this time. The gauge pressure at section 1 is 464 kilopascals, so gauge pressure, and the nozzle discharges to atmosphere. And we want to use these facts to calculate the force in the bolts that attach the flange to the pipe and hold the nozzle in place. Now, before we do this problem, I just want to talk about one common assumption that you can make. It's important that where a jet discharges to atmosphere here, you can assume that at section 2, the pressure is equal to the atmospheric pressure. So here we can set the pressure at P2 equal to 0 gauge. You can always make that assumption where fluid discharges to atmosphere unless you're getting into unless the fluid is flowing near the speed of sound. So for most applications, practical applications, you can where a fluid discharges to atmosphere, be it water or air or any other fluid, you can assume that at the exit of the nozzle or the exit of the discharge point, the pressure is equal to atmosphere. And that's an assumption we'll be making over and over and over again in the course. It's one of those standard assumptions that's valid. Okay, now remember that the linear momentum equation says the sum of the forces equals the change in the momentum of, it's actually the momentum out minus the momentum into the control volume. So what I've done here is draw the nozzle and the control volume. The control volume's on the outside of the nozzle. It cuts through the bolts and the fluid at the inlet to the nozzle, and it cuts through here at 2 where the water discharges to atmosphere. So 2 is right at the discharge point. And I've applied all the forces on here. So you can see here that we have 0 gauge pressure around the outside of the nozzle, so we don't really need to take care of that. We have the bolt forces here, and I've split it into 2 just because we have 2 bolts in the diagram. So FA is the bolt anchoring force. That's what we're after. We're not going to ignore gravity, so I've added the weight of the nozzle here, and I've added the weight of the water downwards. P1A1 is the pressure force in gauge pressure at 1, and P2A2 is the pressure force at the discharge. All the pressures are expressed in gauge pressure for the reasons that we discussed in the previous slide. It greatly simplifies the calculation. We don't have to deal with the complex pressure, integrating the complex pressure over the outside of the nozzle. In fact, we only have to deal with P1A1. You'll see when we get on in this calculation. Okay, so here's our linear momentum equation. It's the sum of the forces equals the rate of momentum out, right, minus the rate of momentum in. This is a steady problem. It says the flow is steady, so we don't have any storage of momentum term. And we only have one inlet, of course, at 1, and we only have one outlet at section 2. So we get that the sum of the forces equals m.2 v2, that's the momentum out, m.1 v1, the momentum in. And you always got to keep in mind that these v's here, they're bolded, that they're vectors. And of course, the forces are vectors. Now in this case, we only have forces in the x direction, and the flow is only in the x direction, so you don't need to break this up into 2 equations. But as we saw in previous applications, you often break this equation up into 2 equations. Note that I've drawn the x-coordinate on here. The x-coordinate's down. You could pick any direction you want. And remember that value, the symbol u, is the x component of velocity. So let's apply our linear momentum theorem. We have the sum of the forces. Fa acts in the negative x direction, so we have a minus sign here. The weight of the nozzle acts in the positive direction. The weight of the water, pressure at the inlet acts downward, so in the positive direction. Pressure at the discharge acts upward. This pressure is going to be 0, but I've included it just so you can see the full expression. And that's got to equal the rate of change of the fluid momentum. This is the rate at which momentum flows out. This is the rate at which momentum flows in. And we have a steady flow situation. There's no mass accumulating inside the control volume, so the rate at which mass flows in equals the rate at which mass flows out, and I'm just going to call that m dot, which is equal to rho q. That's from conservation of mass. Again, steady flow, no storage term, mass flow rate in equals mass flow rate out. And you're told in the problem that the flow rate is 0.6 liters per second, and we know the density of water at 20 degrees C, so we basically know we can calculate very easily the mass flow rate. So what we're after in this problem is to find these the bolt anchoring force, perhaps to do a stress analysis so you could size the bolts appropriately. So solving this equation for FA here, so I'm just going to move it to the other side of the equation. we get this expression. So FA now equals this expression. I've just isolated FA. And let's stop for a moment and just check before you start substituting numbers in. Check that this makes sense, right? What I've got here now is that the bolt anchoring force increases if we increase the weight of the nozzle. That makes sense, right? From a physical perspective, the bolts are supporting the nozzle. Also, the water in the nozzle, the bolts are supporting the weight of the water. So if the weight of the water or the weight of the nozzle increases, FA increases. That is consistent with sort of a common sense. So I'm happy with that. The pressure at P1 acts downwards. It's going to add extra tension to the bolt. And the pressure at 2, if there was one, if it wasn't zero gauge, acts upward. It's going to reduce the tension in the bolts. So that makes physical sense. So I'm happy with that term. Now here's the interesting term. This term, if you ignore the minus sign for a moment, this term here, just the thing I've circled, we expect to be positive because the water is going to exit the nozzle. Because of the reduced area, it's going to exit the nozzle at a substantially higher speed than it enters. So we expect reasonably that U2 is going to be greater than U1. So the m dot U2 minus U1 is going to be a positive term. The water is accelerating, just like in a jet engine. Air gets drawn in and then gets pushed out, and that provides some thrust. And so because water is being accelerated in the positive x direction, that would require a force, and that force reasonably is going to reduce the tension in the bolts. So that the sign of that term makes sense. So I'm happy with that term. So now we can start substituting in some values. We have an expression that we like, and it's just a matter of being careful and calculating the values. So I'm going to calculate the mass flow rate. It's the density of water times the area at 1 times the velocity at 1. And the area at 1 times the velocity of 1 is the volume flow rate. The volume flow rate is everywhere, of course, 6 liters per second. And so we're taking the density of water at 20 degrees C, 998.6 liters per second. Don't forget that a liter is 10 to the minus 3 of a cubic meter, 0.1 meter by 0.1 meter by 0.1 meter, so 10 centimeters by 10 centimeters by 10 centimeters, and so you get 0.599 kilograms a second flowing through this nozzle. So that's our m dot term here. So now we have the mass flow rate. I've rewritten the expression for our bolt anchoring force. This isn't a chalkboard, so you can't see that expression. So I've just rewritten it from the previous slide. We just calculated the mass flow rate, m dot, and now I'm going to calculate the velocities. The volume flow rate is Q just equals U times A, so we can get the velocity one by taking the volume flow rate divided by the area. And so this is the volume flow rate, which is 0.6 liters per minute. Don't forget to convert that to cubic meters, so times 10 to the minus 3, and then pi d1 squared upon 4. And we're told that the inlet diameter in the problem statement is 16 millimeters. And that gives the velocity at 1 is 2.98 meters per second. We can do the same thing at 2. We have the volume flow rate. It's the same volume flow rate throughout, 0.6. And then we just do the same thing, but it's Q divided by pi d2 squared upon 4. And the diameter of the outlet, you're told in the problem statement, is 5 millimeters. So as expected, the velocity is substantially higher because of the reduction in cross-sectional area, 30.6 meters per second. Next, we calculate the weight of the, so that's the two velocities calculated. Next, we calculate the weight of the nozzle, which is just mg. We're told in the problem statement that the nozzle weighs 0.1 kilograms, so times 9.81 meters per second squared, and a kilogram meter per second squared is a newton. So we have the weight of the nozzle. And the weight of the water, you're told in the problem statement that the weight of the water is 3 times 10 to the minus 3 kilograms. times 9.81, and we get this 2.94 times 10 to the minus 2 newtons. That's a pretty small number, normally negligible, but I'm included it here just to demonstrate how you might include the weight of the water. In another problem, if we had a very big nozzle, for example, it could be significant. So now we can calculate the bolt anchoring force. Here's, I've included the calculation with these pressures. We know the inlet pressure is 464 kilopascals gauge pressure. And so we have, there it is, the FA is equal to the weight of the nozzle, the weight of the water, which is small. Here's our P1 times the area at 1, pi d 1 squared upon 4. Then minus the pressure at 2, which is 0 because we're working in gauge pressure. I could have left that out, but I just include it to demonstrate where it would go. If that pressure was not 0, then it would become a negative value. And then you've got minus m dot times the change in the velocity. This is the momentum term, the change in momentum of the fluid as it passes through the nozzle. So I've put the numbers in here, the weight of the nozzle, the weight of the water, which is negligible in this case, the pressure force, the net pressure force on the nozzle, and then that thrust term, which actually acts in the negative x direction because the water is accelerating. But it's not enough to overcome the other forces, so we end up with a positive force in the x direction. So the bolts are going to be in tension. You can't take the bolts out. The bolts have to be there to hold the nozzle on, even with the acceleration of the water. So that's how you calculate the forces on a nozzle. This is a fairly complex example, but I think it's fairly straightforward. This little slide has nothing to do with impulse momentum. I just thought it was kind of interesting, and it relates to wingtip vortices that we talked about in a previous video.